An assertion from educator Carlos Zeros on Durham School. I've committed my entire calling to engaging in an unequivocal speculation about the universe. Then, at that point, this happens, the speculation is being watched out for. I embrace this test because it is through such looking that we advance and gain ground in science. The James Webb Space Telescope is basically disturbing some extended-held convictions in cosmology that have been seen as truth for quite a long time. One more ultra-trackdown pie has uncovered that we have committed mistakes in space science. The telescope, which was wanted to uncover the focal stars of the universe, is actually hazardous. The previous point of view could introduce an absolutely new valid perspective. Not all experts are regretful about these new disclosures. Various specialists are welcoming these levels of progress since it has, for a critical time span, been certain that there were issues with our previous speculations. The abnormalities in reviewing the universe versus speed of improvement alone should have brought alarm bells up for any experts an incredibly long time ago. As opposed to unequivocally loosening up these cautions, a large number adhered to old speculation. The astronomical microwave background radiation, CMB, which is the most obsolete light in the universe, was made around 380,000 years after the Big Bang, when the universe had adequately cooled for electrons and protons to approach stable hydrogen particles. This change, known as reionization, made the universe clear to light. The CMB was first recognized in 1964 by American physicists Arno Penzias and Robert Wilson while they were managing new radio equipment. They encountered a consistent fuss coming from each direction. This discovery was initially considered strong confirmation for the hypothesis of the universe's origin. Penzias and Wilson were awarded the Nobel Prize, and their revelations became a critical foundation in the historical scenery of space science. The CMB in all probability provides a brief insight into the early universe, with minute temperature changes offering essential snippets of data about the conditions not long after the immense blast. Specialists used the CMB as a dependable marker to measure immense pieces of the material universe, including the universe's expansion rate. Edwin Hubble had previously made such assessments in the late 1920s. He saw that faraway enormous systems were making some distance from us every which way and that their speed was associated with their distance, a relationship now known as the Hubble law or the Hubble constant. Notwithstanding the reality that Hubble's assessments were not as accurate as they are today, they were significant. At the point when the CMB was tracked down, subject matter experts recalculated the expansion rate, seeing it as essentially lower than Hubble's basic evaluation. Resulting recalculations using type Ia supernova as standard candles gave a more definite check. In any case, errors remained, and the difference in expansion rate checks has been known since the 1990s. Experts have speculated that there may be issues with the CMB data examination methods or the possibility of general advancement. This uniqueness, known as the S8 tension or Hubble strain, suggests that how we interpret the universe may be fundamentally inadequate. Since the James Webb Space Telescope, JWST, started its operations, it has provided marvelous data that could help with understanding the issue. Worlds so old and mature that their arrangement may theoretically have begun before the Big Bang are testing old scientific speculation. Space science by now faces what is considered to be the greatest crisis in modern cosmology. The expansion speed of the universe and the speculation of how things came to be are under extreme examination. New pictures uncover a universe that differs in an overall sense from past models. The S-strain has served as an early warning, with experts who still adhere to old hypotheses now grappling with the realization that how we interpret the universe may be insufficient. This weakness has left many inspectors lamenting and disheartened. To address this crisis, we must appreciate how science functions. Speculative scientists use a blend of mathematical models, observational data, and reasonable reasoning to arrive at conclusions. Their knowledge comes from seeing anomalies, test results, and speculative analysis. The term speculation itself suggests improvements and considerations rather than outright facts. Our reasonable data comes from pictures provided by telescopes, sound waves, and radiation received by radio telescopes, as well as data from neutrino and gravitational wave detectors. The James Webb Space Telescope grants us to isolate the most established light into individual frequencies and analyze it in remarkable detail. It can show what parts were present in massive systems billions of years ago, the mass held inside them, and the number of stars present. In any case, the Webb's photos may have limitations. For instance, it can't effectively recognize systems or black holes that produce practically identical brightness due to gravitational lensing. Our understanding has progressed to consider different possible results, often dismissing alternative explanations. New discoveries from the James Webb Space Telescope offer critical signs that could prompt replacing old hypotheses with new pieces of information. Specialists are presently grappling with these revelations, which seem so extraordinary that finding new explanations is proving challenging. The latest disclosures are shaking the underpinnings of physical science, causing concern among various experts. Physical science norms today are still strongly influenced by Isaac Newton's 17th-century work. For a significant time, his laws of motion and gravity have provided the foundation for understanding reality and the universe. Newton's laws work brilliantly under typical conditions on Earth. However, in space, his concepts were extended to an extraordinary degree, accomplished by Albert Einstein during the 20th century. Einstein's special theory of relativity, published in 1905, changed how we could interpret reality, showing that the laws of physical science are relative to the observer's motion. His general theory of relativity, published in 1915, expanded these ideas with mathematical measures of gravitational anomalies, considering the bend of spacetime caused by masses like stars or galaxies. While Einstein's theories were proven in various areas, he saw their limits and sought a unifying framework without success. No scientist has yet succeeded in this attempt. It is fascinating to consider where the errors could lie. Michio Kaku, a prominent American astrophysicist, proposed that solving this issue could lead to a Nobel Prize. "We truly need to explore what reality might have been confused," he said, "whether there have been misinterpretations of anomalies or if telescopes themselves might be at fault. Dark matter and dark energy are top suspects in the cosmological crisis. Current models suggest that dark matter and dark energy together account for at least 95% of the universe, yet neither has been directly seen or proven to exist. They may not exist at all or perhaps have properties we don't yet understand. One possibility being examined is that dark matter's properties might have evolved over time, potentially showing some kind of intelligent gravity, which should cause an attraction through mass or spacetime. However, it has not been definitively shown to act exactly as expected. Nonetheless, the reality of spacetime curvature, as outlined by Einstein, has been supported multiple times. We cannot completely dismiss the possibility that gravity has extraordinary properties or that another effect is causing gravitational attraction over time. Specific constants in cosmology and space science have been established as central principles, recognized as reliable largely due to their consistency. Assessments suggested that small variations in these constants could offer new insights into the universe, possibly unraveling anomalies. Without dark energy, it is also possible that our interpretations of light shifts have been incorrect, leading to mistaken distance estimates in galaxy ages. Perhaps our assumptions about the universe's conditions were flawed, or we misread the cosmic microwave background radiation. It could even be that the universe doesn't originate from a single early phase, challenging the Big Bang theory. Minor errors in the Webb telescope or other observational instruments can't be ruled out. Specialists and scientists recognize that mistakes in instrumentation, data handling, or interpretation are always possible. The continuous reassessment of cosmological theories highlights the fundamental nature of scientific progress, the ability to change, challenge, and refine our understanding based on new evidence. The James Webb Space Telescope's insights are more than a technological leap. They represent a significant moment in our quest to unravel the universe's deepest secrets. As we wrestle with these revelations, it is essential to see the broader context and implications of such fundamental changes in cosmology. The approach involved is often driven by the need to refine theories in accordance with new experiences. The discovery of curious anomalies or inconsistencies in established theories can be unsettling, but it also presents a critical opportunity for intellectual development. Hypothetical models in cosmology are constructed to provide a clear framework for understanding the universe's origins, evolution, and development. However, as new data emerges, these models must be tested and, if necessary, revised to accommodate new findings. One critical area of focus is the nature of dark matter and dark energy, which are crucial to contemporary cosmological models. Dark matter, an intangible form of matter that does not emit or absorb light, was proposed to account for discrepancies between observed galaxy rotations and the mass predicted by visible matter alone. Similarly, dark energy was introduced to explain the observed acceleration of the universe's expansion. Yet despite their foundational roles, both dark matter and dark energy remain elusive, with research on Earth still failing to definitively identify them. This has driven researchers to explore alternative hypotheses and possible explanations. The challenge of understanding dark matter and dark energy is further compounded by the vast scale involved in cosmological observations, including distant galaxies, cosmic microwave background radiation, and other grand anomalies, which offer indirect evidence of these components but remain elusive in their precise nature. This uncertainty has prompted scientists to consider a range of theories, from modifications to existing models to entirely new principles. A few theories suggest that dark matter could be made up of more exotic particles than previously thought, or that dark energy might represent an entirely new fundamental force. Another intriguing area of cosmological study is the investigation of cosmic inflation. This theory posits that the universe underwent rapid expansion in its earliest moments, leading to the vast-scale structure we observe today. While inflationary theory has successfully explained many aspects of the universe, like its homogeneity and flatness, it also raises questions about the nature of the inflationary period itself. Insights that challenge established models of expansion could lead to revisions in how we interpret the universe's early history. Finally, the search for extraterrestrial life remains a driving force in space exploration. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened new avenues for considering the conditions necessary for life. Advances in telescope technology, such as the James Webb Space Telescope, allow us to explore the environments of these exoplanets for potential biomarker signatures. The possibility of finding life beyond Earth carries profound implications for how we interpret the universe and our place within it. In conclusion, the reassessment of cosmological theories reflects the strength of the scientific method. The James Webb Space Telescope and other high-level scientific instruments have provided groundbreaking insights into the universe, prompting experts to revisit and refine long-held hypotheses. This process of continual inquiry and revision is vital for advancing our understanding of the universe and resolving the fundamental questions that lie at the heart of cosmology and space science. As we continue to explore the cosmos, we remain engaged in a quest for knowledge that not only seeks to answer key questions but also inspires future generations to push the boundaries of human comprehension.